Now we have to pick the next assembly instruction to look at, and I'm going to choose the CADDI for SBN because it sounds similar to the CADDI that we just looked at. So there is a diagram in the optional book for this class, which I find extremely helpful at figuring out what the names are of things. So we've got this CADDI for SBN, and we want to figure out what is this. Well, we basically take that and we line it up here and we go down the line and say, does it equal one of these rows? So the first thing is C.add I is one option, and this underscore means nothing. So you can have a C.add, that is a valid compressed instruction, and C.add I is also a valid compressed instruction. But that is not what we're looking for. We're looking for C.add I for SBN. So moving down, C.add I 16SP, nope. That's not it. And C.add I for SPN. Bingo, that is exactly what we want. So that also tells us the name. What does this thing stand for? Compressed add immediate times 4 to stack pointer non-destructive. All right, let's break all that up in a little bit. But basically, the C.add I for SBN will ultimately expand out to just this. Add I S0 SP16. So it expands to this. It's just the compressed form. Now, if you don't have the book, which is fine, you can just search and find all the descriptions and definitions in the manual, of course. The one downside of the manual is that, at least as far as I've seen thus far, it doesn't seem to actually spell out the instruction mnemonics that way, the way that diagram does in the book. And that means that essentially, as far as I can tell right now, if you just looked in the manual, you would never really fully understand that C.add I for SPN stands for add immediate times 4 stack pointer non-destructive. Like, there are hints of that in here, but it's not just all spelled out like that. So that is why I like that diagram from the book. Okay, so let's break it down now. It's compressed add instruction times 4 to stack pointer non-destructive. If the instruction is immediate times 4, as it says right here, and if I'm reading an assembly instruction that has S0, SP, and 16, we are left with some ambiguity of, is this immediate multiplied times 4? Or is a smaller immediate of 4 already multiplied by 4, and then the disassembler is just telling us 16 because it already calculated the 4 times 4 to get 16. So that's ambiguous, and we kind of have to dig into the actual encoding and definitions and documentation. I don't really want to cover that this early in the class, but unfortunately, in order to understand what's going on with these compressed instructions, we kind of have to. Okay, so I said that this particular thing, C.add I for SPN S0 SP16, expands to add I S0 SP16. So that add I does not have a multiplication, and so if I'm saying it's 16, well, that means it must be 16 is the ultimate value that's added to stack pointer, not 16 times 4. But that still leaves us with ambiguity in terms of, is the actual 16 encoded into the assembly instruction, or is the disassembler, again, hiding the fact that there's a 4 there and then it's multiplying it times 4 and giving us a 16 to display for the human to make a nice. And again, we can only really figure that out if we drill down and actually dig into how the C.add I is actually encoded. So let's go ahead and zoom in on this. There is an element here that is going to recur in other compressed instructions, and that is this portion here. It says that this is scaled by 4, and that's what it means by that immediate times 4. So it's saying it adds a 0 extended non-zero immediate scaled by 4 to the stack pointer. Now that non-zero unsigned or 0 extended immediate is these 8 bits right here. But if we look carefully at these 8 bits, we can see that while it tells us, bit 9 and bit 8 and bit 7 and bit 6, it is not actually telling us all possible bit values. We fill this in from this, so bit 5 comes first, bit 4, next, bit 9, 8, 7, 6, 2, 3, but there is no mention and there is no room for bit 1 and bit 0. So if we break this out and we do our little decoding here to figure out, what this ultimate 10-bit value is going to look like, it's 10-bit because it has immediate 9 is specified here, bit 9 is specified, and so if there's up to bit 9, index 9. That means it must be a 10-bit value overall. So this 10-bit value has 8 of the bits specified, but the bottom 2 bits are left unspecified, uncoded in here. And this is what this scaled by x really means. It said it was scaled by 4, and that means that actually it's going to leave the least significant 2 bits as implicitly 0, and the value you're actually encoding with 8 bits is a 10-bit value, that is multiples of 4. So scaled by x really means you can only encode multiples of x. So let's see that concretely. Okay, here is our code, and if we use the disassemble/r option, it'll give us the actual opcode bytes that are used to encode the instructions. We're going to focus on the CADI for SBN, and that shows us that it has bytes 00 and 08. Now at this point, we don't know if the disassembler is actually showing this little endian order or big endian order. So to remove any ambiguity, we go ahead and do a hex display. So we display memory as one half-word 16-bit value specified in hexadecimal format. So if we do that, we get this, a 16-bit value where the most significant byte is 08 and the least significant byte is 00. So there's no ambiguity there. It's always sort of big endian order once you see a value like this. All right, so go ahead and fill in that 0800 in hex. So 0, these 4 bits are the most significant 0. These 4 bits are the 8, 0, and 0. So we fill in all those bits. We transfer them down into immediate bit 4 and 5 and 9 and 8 and so forth. And so putting all of those bits through, what we get is bit 0 is hard-coded to 0, bit 1 is hard-coded to 0, and then bit 2 comes from this 0, bit 3 comes from that 0, and bit 4 is the 1 that came from this hex nibble 8. So that 1 transfers through, and that ultimately leaves us with this 10-bit value. 10-bit value encoded with only 8 bits, and the least significant 2 bits hard-coded to 0. If we interpret those binary digits as hexadecimal, we get the least significant nibble. 4 bits of 0 is 0. 4 bits of 0001 is 1, and upper 2 bits of 00 is 0. That gives us hex 10, which is decimal 16. So this is the actual 16 that we see encoded in the assembly instruction here. And how is it actually encoded behind the scenes? You could say this is encoded as 4, like if you ignore the fact that there are these 2 implicit things, the actual value here is 4 in some sense. But you can also see that it's not like just straight up encoded as a 4. There's no like 0, 0, 1, 0, 0, 0, because all these bits are all scattered and rearranged in their order. So basically, I would just treat it like, look, it's encoded as a 10-bit value. The bottom 2 bits, because it says scaled by 4, are actually a 0 and 0. And just when you look at the encoding, you can see there is no 0th bit, there is no 1th bit. So ultimately, it is just encoding decimal 16, hex 1, 0. And so we'll see this scaled by x thing occur multiple times. And whenever you see a scaled by x, you can just treat it as, well, if they say scaled by 2, that means the least significant bit is 0. Scaled by 4, 2 bits are 0. Scaled by 8, 3 bits are 0. Scaled by 16, 4 bits are 0, and so forth. But if you look at the actual, description, it'll ultimately become unambiguous. Of course, this is why we wanted to leave reading the fun manual till later on, and we will come back to it again, but we're going to just keep trucking with these couple of compressed instructions just for now, just because they're going to keep coming up as we use Scarlet Witch's power to blast away the aliases, instruction aliases. We're going to keep seeing these, so we kind of need to cover them early on in the class. But back to covering what exactly this instruction does. So we've got the 0 extended non-zero immediate. So it's telling you can't encode a 0 here, otherwise that's going to be considered invalid. And it's also unsigned or 0 extended. So it is 0 extended before you add it to the register, before you add it to the stack pointer register, and before it's placed into the destination register. But there's also that element at the end of here where it says non-destructive. So what does non-destructive mean? Well, it means that it's adding to the stack pointer, and it's actually hard-coded that it adds to the stack pointer before putting it into the destination register, but it is not like adding to the stack pointer in a way that changes the stack pointer. It's just add to the stack pointer and put it in, some temporary, like actually hidden register that you, the assembly programmer, can't see. So it places it in a scratch register, calculates the value, and stores that value into the destination without ever actually changing SP. So this is how I would kind of describe this instruction using the conventions we use in this class. We have add for SBN. We've got the destination RD prime. RD prime can only be specified by 3 bits, so that's going to be some subset of the 32 possible registers. You can't encode all possible 32 registers in only 3 bits. So some subset of registers, and take SP plus your non-zero, zero extended, 10-bit immediate. That is also scaled by 4, as we saw. And the key thing is this is not actually going to memory at stack pointer plus 10, so we're not dereferencing memory. There's no parentheses here to indicate that we're dereferencing memory. Just stack pointer plus immediate goes into the destination register. As I said, the RD prime can only be so there's only 3 bits, and they've chosen to say that the encoding of those 3 bits will encode X8 through X15, also known as S0, S1, A0 through A5. And then we saw that the non-zero, unsigned, or zero extended immediate 10 is scaled by 4, so the bottom 2 bits are implicit zeros, which means only 8 bits are actually used to encode this 10-bit immediate. All right, with that, we have checked off the C add for SBN non-destructive. So add immediate times 4, so really just an immediate that's encoded in a way that it must always be a multiple of 4. Immediate times 4 to the stack pointer, non-destructive, so we're not changing the stack pointer, we're changing whatever the destination prime register is here.